And welcome back as we continue our cosmic journey. We previously had talked a little bit about the Earth as a sphere and some of the different layers within the Earth. And one of those layers was, of course, the crust. So let's go ahead and take a little bit more deep dive into what that crust actually is and what it does for us. So let's start by talking about the composition of the crust. Now we, of course, had talked about two different types of crust, but what does it actually mean to have those different layers? Well, as we mentioned, Earth's crust is largely made of either oceanic basalt or continental granite. Now, both of these are examples of what we refer to as igneous rock, which is the term used for any rock that is cooled from a molten state. Now, all volcanically produced rock is igneous rock, but igneous rock is not the only rock that is on Earth. We also have sedimentary and metamorphic rock. The other two kinds of rock that are familiar to Earth, although it turns out that neither is really common on other planets, and there's a reason for that. Sedimentary rock is made from fragments of igneous rock or the shells of living organisms deposited by wind or water and cemented together without melting. On Earth, these rocks include the common things such as sandstones, shales, and limestones. Now, metamorphic rock is produced when you have high temperature or high pressure. That goes ahead and alters igneous or sedimentary rock either physically or chemically. Metamorphic rock are produced on Earth because geological activity carries surface rocks actually back down to considerable depths, and then it will eventually bring them back up to the surface. Without such activity, these changed rocks would not exist at our surface. Now, there's one type of rock that you may not have heard to, but it does not exist on Earth, which is that of primitive rock. This is a very important category of rock that can actually tell us much about the early history of the planetary system. Now, primitive rock represents the original material out of which the planetary system was made, which has largely escaped chemical modification through heating. Now, because of Earth's geological activity, no primitive material is left on Earth, because the entire planet was heated very early on in its history. If we actually want to find primitive rock, we actually have to look to small objects such as comets, asteroids, and even small planetary moons to kind of get a better vision of what primitive rock might look like. And we can actually sometimes see primitive rock in samples that fall to Earth from these smaller objects. Now, one of the things that is unique about Earth's crust is plate tectonics. Plate tectonics really kind of explains how slow motions within the mantle of the Earth move large segments of the crust, resulting in a kind of gradual shifting and drifting of the continents, as well as the formation of things such as mountains and other large-scale geological features. Plate tectonics is actually a mechanism for Earth to transport heat efficiently from the interior, where it's accumulated, out into space. So it's actually a cooling feature. Now, all planets develop a heat transfer process as they evolve. It's just natural. For example, we mentioned previously that Venus has kind of more of a blob tectonics. So those mechanisms can vary from how they might be on Earth because of the chemical makeup and other constraints. So when we actually look at Earth's plates, we can see that the crust and upper mantle are divided up into about a dozen tectonic plates. Now, in some places, such as the Atlantic Ocean, we'll find that those plates are moving apart. In others, such as off the western coast of South America, they're actually being forced together. The power to move the plates is provided by the slow convection of the mantle, which is a process by which heat escapes from the interior through the upward flow of warmer material and the slow sinking of cooler material. And so, as we mentioned, these crusts are either pulling apart or they're coming together. And so one of those ways these happen is through rift and subduction zones. Plates that pull apart from each other happen along rift zones, such as the Mid-Atlantic Ridge, which is driven by upwelling currents in the mantle. What happens is that molten basaltic rock rises from below to fill the space between the receding plates. And when that material comes up, its course is going to form a new plate, and these plates inadvertently then become the youngest plates, because you're not going to have a gap there that's just going to be left open right to the middle of the Earth. Instead, these gaps, when they open up, immediately are going to fill with material. Now, when two plates come together, such as in South America, one plate is often forced beneath another in what we call a subduction zone. So it's forcing the other plate underneath it. And in general, the thicker continental plates cannot be subducted because the material is more, but the thinner oceanic plates, because they are often younger, can be subducted. Now, subduction zones often mean the end of that particular plate as it's then recycled back into the mantle. Now, we have another thing to talk about, which is that of fault zones. Now, fault zones are another thing that might be something that you might notice, and you can kind of see here in this picture where the Earth's kind of jagged along here, because along much of their length, the continental plates are actually going to slide parallel to one another. And when these continental plates slide, they have boundaries, and these boundaries are typically marked by cracks or faults. Now, the motion along fault zones does not take as smoothly as the creeping motion of the plates. Kind of builds up stresses in the crust that are released in sunbound slippages that generate earthquakes. Anyone, for example, that is in along the San Andreas fault line might know this. The longer the interval between earthquakes, the greater the stress, and the more energy released when the surface finally moves. Because just kind of think about it as if you took your two hands, you push them together, and you slide one hand, slide one up, down, the longer you hold those, the more stress it's going to be on your muscles. So when you finally release that, it might be a lot more violent than if you just had it slip past right away. Same thing's happening here with the Earth. The longer over time that those plates are pushing on each other, the more potential energy they have when they finally release. Now, of course, we can't talk about, plate tectonics without talking about mountain building. When you have two continental masses that are moving on a collision course, they're pushing against each other under great pressure. We already talked about, of course, faults and subduction zones. Now, the Earth itself, when these things happen, is either going to buckle, it's going to fold, it's going to drag some rock deep below the surface, and it's going to raise other folds to heights of many different kilometers. This is actually the way many of the mountain ranges on Earth were formed, because they're actually collisions of different plates. Now, once a mountain range is formed, its rocks are subject to erosion by either water or ice. Believe it or not, the sharp peaks and serrated edges that you find often on mountains have little to do with the forces that actually make the mountains initially. In fact, most mountains are actually very smooth when they're originally formed. And instead, what happens is the processes that tear down the mountains, so the wind, the water, the rain, are actually creating these sharp, jagged edges that we often associate mountains with. And of course, not all mountains are formed by plate tectonics. Some are formed by volcanoes. Now, volcanoes are pretty unique things that they mark location where lava is going to rise to the surface. Now, mid-ocean ridges, which are long undersea mountain ranges, are formed by lava rising from Earth's mantle at plate boundaries. Now, you can have a second major kind of activity, which is associated with subduction zones. So when a plate is forced on another plate, you might have some volcanoes appear in those regions where the continental plates are colliding. Now, volcanic activity can also occur above mantle hotspots, which are areas far, far away from plate boundaries, and where heat is nonetheless rising from the interior of the Earth. Of course, the most famous of this is the Ring of Fire in the Pacific Ocean, where you have places such as Hawaii, which are rising up. In each case, though, volcanic activity gives us a way to sample some of the material from deeper within our planet, because it is, of course, having to move from the mantle up onto the surface. Now, not all volcanic eruptions can produce mountains. This might be a misconception you might have, because sometimes that lava flow, if it happens super quickly, it's coming along a long crack. So let's say your entire fault line just burst out into lava. It can actually spread out to form what we refer to as lava plains.